Okay, so in our previous example, we saw the first trig substitution we've learned so far, and we need to analyze exactly what's going on in there, okay? Because it is not a normal type of substitution. In fact, it has a new name. It's called an inverse substitution, okay? So keep in mind that the original u-substitution rule reads like I have in this line right here, okay? You want to take an integral of a composition of functions, f of g, and you've got the derivative of g sitting on the outside. Then you can let u be a new variable, which is that inside function, and do this. Okay. Now look at what I did up here. I did not say let theta equal some function of x, and that's exactly what the theorem for u substitution calls for. Okay. So actually, if we wanted to think about how we did this problem and justify it in terms of u substitution, then what we actually need to do is come back up here to this step right here and specify exactly what we mean. So what I actually mean right here is let theta equal inverse sine of x. That's what's actually going on here. U has to be a function of x. That's the key here to making this u substitution work. Okay, so in other words, up here, my theta has to be a function of x. Okay, and so you can see that this line is not quite all there is to the story, because if you just said sine theta is equal to x, that's not a function of x, because sine isn't a one-to-one function, right? That's the whole reason why we had to specify the bounds on the domain in order to restrict the domain to make sine one-to-one, so that we could do things like talk about inverse sine or arc sine, okay? So properly, to understand what we actually did here, we started off with a function of theta, a function of x, and then we let x be some sort of function of theta, and that's the key right here. It's not that x is a function of theta that's important, it's that theta has to be a function of x that's important, because look at what we've done right here. I've just swapped the two sides of this u substitution rule. Okay, so actually the u in this example is not theta. The u in this example is x, if you're thinking about a normal u substitution. Okay, so we're reversing. We're going backwards through an equals sign in the theorem of u substitution to make this happen. So that's one part of the reason for the name inverse substitution. The other main reason, though, is that this right here, again, theta needs to be a function of x. Okay, our new variable there has got to be a function of the x there. Otherwise, it doesn't uniquely define a theta value, because what a substitution is it should be a way to change x values into theta values, or x values into u values, and vice versa. And this does not specify how to do that. Okay, so one way to fix it is to talk about doing things this way, using an inverse trig function, but that makes things really rough, because if you were to actually do the derivatives here, you would be taking derivatives of like inverse sine and stuff, and it would be just kind of messy. It would work, it would be true, but this is much easier right here, because people more commonly think about the derivatives of, the trig functions rather than the derivatives of the inverse trig functions, which are very new. We've just learned about those. Okay, so here is one important point that a lot of you might take advantage of for providing your critiques. when the students write this, what they really mean is let x equal sine theta, but restrict the theta value to between minus pi over 2 and pi over 2, or in other words, exactly what we had to restrict the domain of sine to be. Okay, so let's put this right here up in blue, where our theta is between minus pi over 2 and pi over 2. Okay, so to properly talk about the substitution, you either need this line plus my blue, or just do it all in terms of the red. But remember, doing it in terms of the red ink here is going to make it much more difficult. All right.